Good morning, Irvine.
Morning.
How are you guys this morning?
Splendid.
Well, that's a good way to be. Splendid is a nice answer for today. I put this cartoon up because sometimes early in the morning, a little humor is a good idea. I have this up on a bookshelf in my laboratory to just give me a little extra motivation for some of those early mornings myself. Oh well. So anyway, lots of Newton jokes out there, right? Okay, so let's see. I need somebody, I need a male wearing a short sleeve shirt. Excellent. Would you assist me, sir?
Sure.
Are you comfortable standing on your head?
No.
With a little help and balance, can you do it for a half a minute? You can do it. Come on down, we'll find out. If he passes out, we'll give him a higher grade. Okay. All right, so let's take some measurements. I'm going to work right here. You can do what you want. So let's take some measurements. You are?
Val.
Val? Hi, I'm Roger McWilliams. We're going to have you here for now. What have I got here? Can you tell? It's a blood pressure meter. What are those things called? Sphygmomanometer. A sphygmomanometer, that's it. So, okay, some kind of meter, right? And this is a healthy specimen here. Okay, give me your arm. We're going to take his blood pressure in a number of ways, okay? So, here's our first way, and we're just going to turn this sucker on and let it do its thing. Come on, do your thing. It's pumping. Do you feel it pumping?
Yeah.
So it's putting air pressure to reduce the flow, block the flow, and also it's got some kind of sensor that can listen in. I'm not sure what it senses. I don't know how. It's going to give us a couple of numbers, systolic and diastolic. I don't know what those mean. So one of them is like a maximum blood pressure when the heart is pumping, and the other is like the minimum blood pressure when the heart is pumping. And we're going ahead and taking a measurement. We're taking a measurement, and we got one, okay? So we got a systolic at 130, 132, and a diastolic at 98. We got to put you on beta blockers. And so, depending on what kind of activity you have, and if you're revved up and going and stuff, your blood pressure will be higher or lower over the course of the day. Now, we've taken a number right here, Val?
Yes.
With Val's arm at about the same as his heart level. So now what I want to do, that's 132 over 98. You got it? Okay? All right. Arm up, up, up. Now let's try it again and see what we get. What do we expect to get? If we make a prediction, right, guess the answer, we expect that now there's less pressure because it's higher up the column of blood. And we could make a prediction about how much higher up he is, what the blood pressure would be, because by how much was this meter raised? Uh-oh, it says error. It's not happy doing it that way. So let's, I'll help hold it up and see if that works. So if we're raised, what are we raised? About a quarter of a meter up there? And it might work this time, we'll see. And then what we're going to do is have him stand on his head and have the gauge down at the bottom. It kind of sounds like it's working, so I'm optimistic. It said he died. It gave an error message. Doesn't want to do it up there. Okay, so now let's get him. Yeah. Yeah, but I want to get it all the way up there. So now we got to take your glasses off probably, right? And any valuables? Yeah. Anything else going to fall out when you're upside down, you think? You're cool?
Yeah.
Your pants will stay on and all that, right? Okay.
Should.
So what I thought was if we balance you against here, you should be okay, right? So let's try and get you up on your head. Just go ahead. Keep going. I'll help you out. Okay. Which way do you want to do? Do you want to face people or do you want to face the wall?
Face people.
Face the people?
No, not face people.
Okay, let's just go. Here we go. Ready? Get on the head. Oh my goodness. Somebody come push the button. Come on, hurry up. He's got about a minute down there and then he's going to get unhappy. Hey, we got the right angle that you're suggesting, don't we? It says it's working. Are you okay, Val?
Yeah.
If you say you're not, I'll let you down, but let's try to go for it if you can. Oh, dear. I hope it works. I hope it works. It's still moving around. Oh, dear. No, it looks like it failed. Okay, coming down. Oh, man. Wait a minute, now we're all tangled up. Okay. Okay, error 5. Apparently it doesn't want to do that measurement. Let's, how could we, we could abuse Val some more. Come over here, Val. Can you, lie down along there and then put your arm down here. Let's see if we can get it. I want the arm lower than the body. Let's see if we can get it there. That won't do too much for us, right? Are you cool?
Yeah.
All right, in fact, with the cement there, you're very cool. Okay. Oh, this won't be that different, will it? The patient is lying on the stretcher, the gurney, whatever. Should we splash some ketchup on you or something, make it look real? That's a little better, isn't it?
Yeah.
You did a fantastic job there. I don't think I could last that long on my head. Okay, so apparently this machine, I haven't obviously tried that machine in those conditions before, but apparently it gives such wild readings that it realizes there's something wrong and it gives an error message instead of giving us numbers. We'll do a calculation for what we expected it to have been anyway, okay? The stress of it, it went up, right? Okay, so this thing isn't gonna do what I wanna show you. Uh-oh, now I broke it. Okay, Val, thank you very much. Excellent job on Val's part. Okay, so let's see now. I want to do a calculation for that, but I suppose I want to show, we can do it in a sensible order. Okay. Have you helped?
Yeah.
Have you helped? Have you helped? Why don't you help then? We'll get you next. Is that good? Okay. Val, cool. Tell your mom to put a gold star on the refrigerator at home. That was a good job. Okay, and you are?
Laura.
Laura, and a little bit trepidation is in her mind now. If he did that to Val, what's he gonna do to you, right?
Sure.
Okay, all right, so this is, why don't you get over here, you're gonna run the demo stuff here. This is a syringe, and it moves back and forth. It has some volume readings on it, 30 cc's, 25 cc's, and here's a pressure gauge over here, right? And it's not a sphygmomanometer. I don't know what it's called though. But I know how it works. That's cool. Okay, so try pushing on the syringe. And what happens, can you guys see the needle on the pressure gauge? Push a little more. What's happening to the pressure? Okay, try pulling the syringe out a bit. And don't go past, like 30 on that thing, or you can look at it either way. Okay, so let's just let it sit there somewhere and let it come to equilibrium and make a pressure measurement. See what we get for a number over there. Pressure, I'll bet that's, what units do you suppose that pressure gauge is in? Could be millimeters of mercury, could be pounds per square inch. Since it's sitting there at equilibrium, I'm guessing it's pounds per square inch, and it's just a little under, 14.7 pounds per square inch is 1 atmosphere, right? Okay, so let's try, and it's reading about 16 cubic centimeters of volume. And so Laura is going to, can you make it reduce to 8, do you think? Can you shrink it down to 8? And hold it at 8, that's 9, 8. Hold it right there. What is the pressure at 8? It's about 23 and a half, right?
14.
What's that?
I don't think it's 8.
It's at 8, it's at 8, it's at 8. Yeah, it's about 8 the way I was reading it from the side. The parallax issues for different places. Okay, so it's reading about 23 and a half, right? And you think you can squeeze it down to 4 or not? Is that going to be too hard? A little more, a little more, a little more. Oh, it's hard to do, isn't it? Okay, I'm not trying to overwork you. Okay, that was at about 36 at 4, wasn't it? Okay, let go. And let's see where it goes. It's at 15. It was at 16 before when it settled in. About there's a little friction. Okay, now can you go to 30, you think, with it? Pulling it out? And keep going, keep going. Let's go to 32. You have to kind of visualize where it would be, right? Can you do it? 32. Keep going, keep going. That's about, I'm sorry. Okay, so we got about 9 there. Okay, good enough. Cool.
Okay.
Do you want to help with the other one?
Sure.
That wasn't so bad, right? He had the hard one, right? You lucked out. Let's see if I can figure out how to do this. Here, that's good. Okay, this is the pressure. Here you go. You're going to hold that, all right? And are you taking good notes for her? Good observations, good drawings of what you're seeing. Okay, Laura, describe to the class what you're holding.
Ball.
A ball. And the ball has a wood handle attached to it, and the tube with the gas that goes over to the pressure gauge is attached to the ball. Is the ball solid or hollow? It's hollow. She says it with confidence because she has experience with the mass density of steel and knows that if it was solid, it would be much heavier than it is now, right? Okay, so how big is the diameter of the ball? Isn't it convenient that everything's about 1 or 10 or, so it's about 10 centimeter diameter on the ball, right? So we could figure out what's the volume of a sphere. Do you remember the symbolic formula? 4/3 pi r cubed, right? Cubed because we got a volume, pi because it adds some elegance, and the 4/3 because it's spherical stuff, right? What's the area of a sphere? The surface area of the sphere that Laura's holding. 4 pi r squared, right? It's got a 4 out front because it's a sphere, not just a surface like a circle. Okay, now, miraculously, do you want to do that? Yep. I don't know how to do this one. It's got all safety stuff on it. I'm going to get one that doesn't have safety stuff. Okay. All right. Did you, we're going to cook that thing a little bit, right? What temperature is this ball right now? Is it room temperature?
Yeah.
Okay, so she touched it. It's room temperature, right? Okay. Now we're going to heat it up. We're going to change the temperature of the ball. And we're going to watch what happens to the pressure as we heat it up. And then the ball's going to get hot. So we don't want you to touch it after we start doing that, okay?
Okay.
And we don't want to set it on here and melt this table. And we don't want to burn the house down. Okay. We'll use some of these guys. If they light on fire, we can carry them outside. Okay. You got to think ahead. But I'm closer to the door than you guys, right? That's the old thing about the two people out in the woods, and there's a bear that comes and is going to attack them, and the two guys start to run away, and one of them goes, I don't know if I can outrun a bear. And the other guy goes, I don't care about that. All I have to do is outrun you. Okay, how fast can bears run? Well, I was east of Hudson Bay one time in an old Willis Jeep out in the middle of nowhere. Came around a corner on a caterpillar cut section, and there was nowhere for anything to go off the road. There was a big bear sitting in the middle of the road. So I floored the Jeep straight at it. Scared the daylights out of the bear. It jumped up and ran, fortunately, away from the Jeep, and it outran the Jeep. The Jeep was in lowercase differential, so lowercase, the highest gear and lowercase differential on that Jeep was 24 miles an hour. So the bear outran 24 miles an hour because I floored it on that sucker. And then after having that amusement, I came to a halt, and the two other gentlemen in the Willis with me said, don't do that again. Okay, so I quantified how fast bears could run, partly, gave it a lower bound. Now let's try warming this guy up and see what happens. We got a pressure reading over there. Oh, look at that. As the temperature of the ball is rising, the pressure inside the ball is rising. Is this exciting beyond belief? Val, don't you wish I picked you for this one instead of the other? But it was very noble of you to do that one. Is this enough excitement on this? Okay, I think that's enough excitement. Okay, so now let's just have you hold it there a second while it cools down just a little bit. And let me take it from you. It's still very warm. Close your eyes. No, close your eyes. I will. Now put your hand down, and I want you to feel the heat just above your lip, between the lip and the nose. What's that thing called? This thing.
Philtrum.
Say it again?
Philtrum.
Okay, the Philtrum. Of course, I knew that. So I had no idea that that's the name of that thing. The Philtrum is very temperature sensitive, isn't it? And you can, with your eyes closed, you can feel the warmth, right? So it's a way to learn about heat that's being radiated, which we need to learn about. That's called black body radiation. So let's see if we can figure that out. Yes, that works. Okay, so if we all, here's what you're going to do. You're going to close your eyes. You're going to stop breathing. Then you're going to put your hand down right in front, and then you're going to raise it back up with eyes closed. When it's right in front, it's like the little Philtrum is looking at your hand. When your hand's moved away, now the Philtrum's looking at the room. And they are different temperatures. Your hand is warmer. Of course, this thing is sitting there. Show them how. If you don't breathe, you can feel the difference. It's warmer on the philtrum, as you call it, than when the hand is there in front of it, not touching, just in front, than when it's moved away. Because the room, I suppose that's not going to light now. Okay. Thank you very much, Laura. Okay. Okay, now let's see. Let's do a calculation or two. Those are fun things too, aren't they? So we saw that for a fixed volume, the pressure went up if the temperature went up. Okay, so we did this Boyle's law, Charles' law kind of stuff, right? Now, and when we changed the volume, we shrank the volume, the pressure went up. When we increased the volume, the pressure went down. So we did not see it do it exactly as 1 over the volume, but we saw something close to that. So this idea of the ideal gas law and the Boyle's law and all that stuff are very good approximations for a lot of circumstances, but don't always get all the little details in that you want to know. But they get pretty good for a lot of things. Okay. Let's go back and think about Val just a minute with a little more on the blood pressure part and get a calculation. So here's this is Val. Okay? It looks kind of like Gumby, doesn't it? All right? Okay, so anyway, this is Val, and there's where the heart is located approximately. So what we were doing was we measure the pressure here. Why do we use the arm to measure the pressure? I'm gonna, oh, it's got to have a few more of these in it. I don't know what it, do you guys know what it is for the right spelling? Sphygno. Sphygno. Okay, it's close to that. We got most of them in there somewhere. Okay, we do it on the arm for a couple of reasons. One, there's good blood going there from the heart. Another one is it's a little less personal, right? It's out at a region you can be less intrusive to the person's spirit in doing that. And then the other reason is you pick it to be at the same height as the heart, so that the pressures are indicative of what's going on in the heart. And so the pressure, if we want to think about the pressure, the delta P to the head is going to be rho G H heart to head. And that's going to be approximately 10 cubed, 10 to the 1. And how high up is it? Maybe 20 centimeters, 2 times 10 to the minus 1. So it's approximately 2 times 10 cubed newtons per square meter. Lower pressure at the head. Lower. At the head. Then let's consider if we want to go to the feet, the delta P heart to feet. Which I was attempting to show with Val's, well, today it was a valiant effort. Thank you, sir. So with the valiant effort, we were trying to do the heart to feet, and that's rho GH, so that's about 10 cubed, 10 to the 1, and the height there is maybe more than a meter, right? 1 meter, let's say, so that's about 10 to the 4th newtons per square meter. So that says that your feet have a lot higher blood pressure on them. That's an increase, right? Higher than the heart. So, for example, this brings to my memory my dear old grandmother. And when she was older, she had a lot of difficulty walking and spent a lot of time sitting in a chair. And her heart didn't work very well, so that the feet would eventually kind of get a little swollen from too much blood. So she had a chair that she could tip, because the blood pressure difference was hard for her heart to pump it back up. And she could tip the chair up and lie flat so that the blood could come back out of her feet a bit better and be a little more comforting for her. So these simple little things about understanding pressure can make quite a bit of difference. In fact, Val, was it feeling like there was a lot of pressure in your head when we had you up on your doing the headstand? Yes. It was uncomfortably high pressure, right? So just the difference of flipping him upside down, the head is used to a few 10 to the fourth lower pressure than what he had when we flipped him up. Now, when you lay down, your head's still on the ground, but the rest of the blood is now lying at the same height, so it's not a column of blood above him, okay? That's why there's a difference there. You can have your head on the ground lying down, no big deal. Sleep all day, right? You can have your head with your feet straight up, and it gets uncomfortable very quickly. Now, how many of you have played with children where you give them a little headstand and they love it, don't they? They don't have as much a distance from the legs to the head, so that the pressure differential across the child's body size is much smaller, 1/3 or 1/4 as much. It doesn't bother them. How many of you have read a book to a child? And you sit them in your lap, and it's so cute, right? And you're sitting there holding the book. Where do you hold the book? Show me with your hands. Where do you hold the book? About here. And the kid is sitting here, right? And their head is this far from the book. And you go, well, it's okay if it's out of focus for them because they can't read anyway, right? It is not out of focus for them. They can focus on it. Little kids can have distance of nearest comfortable accommodation about 9 centimeters. At your age, it's about 22 to 24 centimeters on average. Okay? So you should learn about how eyes work. They're cute. Eyes are really neat. All right, we've got that. Now, oh, the dam. Let's do that. Let's do a little more for Hoover Dam. Hoover Dam power. Electricity is something we are extremely happy to have, and we go to a lot of trouble to have it. So here's a Hoover Dam. It must have a height of 200 meters and a width of about 400 meters. Okay, that's our dam. So your perspective here, you're either in the water or on the other side where if the dam breaks, you're going to be wiped out. That's your perspective, okay? Upstream, downstream from the dam. What is the force on this thing? Let's see, force on the dam. Force on the dam wall. Okay, let's see. If we're going to use that same notation, let's do that, 0 to h. And here's some portion. This guy has some width w, and then it has this little element here is dy. So the force at df is going to be the pressure at y times the area, right? So it's going to be P times W times dy. So the total force is going to be add those guys up, and the pressure is rho g y w dy. Okay, that's what we got so far. I took the constants out. The density water is basically incompressible. Gravity is not changing. I'm saying let's just have a constant wall width for the dam. The dam isn't quite that shape, but it's close, right? So let's see. The total force is going to be rho g w y squared over 2 0 h. So rho g w h squared over 2. So there's our symbolic answer. Let's ask ourselves our questions. If water was denser, would the force be greater? Yes. Okay, it looks like it. If gravity was pulling harder on it and pushing the water down harder, would it be a bigger force? Yes. Okay, so it's upstairs. If the dam was twice as wide, wouldn't we expect twice the total force? Yes. Okay, so that makes sense. And if the dam got taller, don't we expect the force to increase? Yes. But the h squared is a little bit counterintuitive for a lot of people, except that we've already realized, and Val certainly realized, that the pressure up at the top is different from the pressure down at the bottom. So it gets increasingly stronger as you get to a taller and taller dam. Okay, let's put some numbers in. So F total is approximately, it's water, 10 to the 3 kilograms per cubic meter. I'll put some units in here so you see those. And this is 9.8 is 10 meters per second squared. W, 400 meters, I think I said. H, 2 times 10 squared meters squared over 2. Okay. What is 2 squared? 4. What's 4 times 4? 16. What's 16 over 2? 8. 8 times 10 to the 3, 5. Oh, let's see. Is that what we want to do? Right? 4, 6, 9. 8 times 10 to the 9th times 10 to the 1. 8 times 10 to the 10th newtons. Okay, 8 times 10 to the 10th newtons. That's 80 billion newtons. A typical person, say 50 kilograms times G, M times G is 500. We got 500 versus 80 billion. It's a little hard to comprehend that number, isn't it? It's big. But it also means you're not going to want to hold the dam if it's getting a little loose. Okay. How about...
I have a question.
Yes, ma'am.
Sorry, it might be a stupid question, but on the quizzes you said we are not allowed to calculate.
You are correct. On the quiz, you may not...
Approximate numbers.
You've got to approximate numbers just like the way I'm doing it here, okay? I don't need to get 3 digits of accuracy. I don't even need really to get 20% accuracy. I just want to get ballpark. We're doing order of magnitude kind of estimates and practice stuff here, okay? So don't spend a lot of time doing all that, what is that called? Longhand multiplication, longhand division? That is a waste of time for getting your initial estimates done, okay?
I have a second question.
Yes?
What was it that went wrong with the Hoover Dam, with the way they built it? There was the engineer who built it, basically, there was something wrong, so like the concrete inside was expanding.
Oh, I think that there was, something was encountered with Hoover Dam in the construction. It was like one of the world's largest public works projects ever, right? I mean, the pyramids are comparable size, but I think when they were pouring the concrete has an exothermic reaction in the curing and elevates the temperature inside for a while it's doing that curing. And it takes, depending on the size of the volume, it takes from days to years to fully cure. And so I think there probably were some issues with thermal expansion and heat dissipation, and we're going to do some thermal expansion stuff in just a little bit. So it's a good question to kind of ask about. Yeah. Have you been to Hoover Dam? It's way cool. Let's see, let's make the dam work. Dam makes electricity. So here's the water level, here's the dam, and then down here at the bottom somewhere there's a little hole cut, and water comes out and spins generators. Okay, who did I promise was going to be the next demo person? In the lovely, delicate turquoise. And you are?
Christina?
Christina, I'm Roger McWilliams. Come on down and help out. Okay. Let's see now, we got corks in place. I want you guys to take another measurement on this just in case we didn't get it well enough done for you before. And so I want you saw where the three spouts of water went, right? And I'm going to try to do it for a little longer time, in a second time now, so it should repeat, and then you should be able to get good measurements for yourself. Okay, so you know approximately where things are going to go, right? So make your drawing and try to get an idea of how many centimeters out for when it fell to how far. So you could take, the base of this thing and imagine it across here. These tickings on the box are about 7 centimeters each, but you can decide for yourself. And is Christine?
Christina?
Christina. Okay. So Christina's going to pull the plug, and then I'm going to try to keep the water flow steady so you can have it all be steady state while you take your observations, okay? You guys ready? Yeah, pull the corks. You got your measurements yet? Okay, I'm bored. Cork it up, cork her up. Yeah, good job. Thank you very much. Are you dry?
That's okay.
Okay, shake her off and go on up there. Thanks very much, Christina. Okay, that's cool. So what our observation that's relevant to this calculation is, down at the bottom of the water column, that's where it came out fastest, didn't it? So it's converting. We have our Bernoulli's equation. It's got some coating on it that didn't want to write. We got pressure plus a half rho v squared plus rho gh is a constant. So we have that. The water in the column down at the bottom is basically not moving. It's just sitting there. And then outside is 1 atmosphere of pressure. So we have the column of water pressure pushing on that water, and the atmospheric pressure outside can't oppose it very successfully. So the difference in the pressure drives the water out, giving it the kinetic energy as it passes through. So we have that this pressure in the column, minus pressure of the air is a half rho v squared. This is the exit speed. Squared, right? The exit speed squared. That's a bad 2. Okay. So the, let's see. What is our pressure in the column? If we go 1 atmosphere, 1.01 times 10 to the 5th newtons per square meter. Pressure in column, rho g h, all right? Plus the air pressure, because the air was above it as well. So this rho gh, 10 to the 1 for water, G 9.8, and let's suppose we go 10 meters. 10 meter example. (9.8) is about what number? 10. So we have, mistake. Remember the first off, trust no one? What did I put for the density of water there? 10 to the 1. And you let it go. The humiliation. Oh my God. When I make a mistake, tell me, folks, right? Sometimes I'll make a mistake, and it's got to get corrected. Otherwise, you'll go home, look at this thing, and go, I can't get that. I don't understand it. Physics is so hard. Well, yeah, especially if the professor makes a mistake, right? So always judge it and then tell me. And sometimes I'll have gotten it right and your judgment was wrong, and we can sort it out, okay? So this is then 10 to the 5th newtons per square meter. This says that 10 meters of water is 1 atmosphere of pressure at the bottom. 33 feet of water is 1 atmosphere of pressure. That's a number to kind of keep in your mind. 33 feet. If you go to the bottom of an 8-foot pool, you've gone a quarter of the way there, haven't you? And you feel your ears pop. If you go up the mountain, you can feel your ears pop going the other way, right? Okay. So, P. Hoover at the generators. Let's suppose rho g h is about 10 cubed, 10 to the 1, and that the height is maybe 150 meters. All right? Generator height. Generator below water surface. So the generators are below the water surface by about 150 meters, something like that. 3/4 of the way down the dam, and the water level on top of the dam varies, right? So that means that this pressure is about 1.5 times 10 to the 6th newtons per square meter. There are two moments here that I'm thinking of where I try to take a different perspective to see if the thing is right. You notice where I bobbled for a minute up above, and I said 10 meters of water, and with the 10 to the 1 there, I got a 10 to the 1, 10 cubed was my answer, and I knew the answer was 10 to the 5th for 10 meters of water. And I'm going, oh, judge your answer, McW. It's not right. Okay, and then you go back and find your mistake in that case. Now, for the Hoover generator, 150 meters then is 15 atmospheres. So is this 15 times 1 atmosphere? Yes. 150 meters is 15 sections of 10 meters of water. So we can judge it by the physics without knowing the numbers and say we expect it to be bigger by about an order of magnitude. And then we can get our numbers and we go, okay, yes it is. Okay, so this number, that's a lot of pressure. Hence, the concrete has to be really strong and really thick. You see these 3 little dots here? Somebody must have punched the chalkboard in irritation at some point. It's 3 knuckles. It exactly fits somebody's knuckles. Bad idea. They must have been doing something other than physics. Because physics is so fun. Okay, so now we have P plus a half rho V squared plus rho G H is a constant. So now what I want to do is, at that 150 meters deep, let's let the water out. Water out sideways, right? Through the hole, through the generator. As the water's going through the generator, let's think about the physics side of it. As the water's going through the generator, is its elevation changing? No. The water going through the generator is staying at constant, we're using y in that equation, constant y. So what we have is the same thing as that little demo with the tube we just did with Christina, and I don't remember who the fellow was who helped yesterday. So anyway, we have pressure is getting converted then to a half rho V squared. So this number is equal to 1.5 times 10 to the 6th, and this is newtons per square meter. But let's let this equation talk to us. A half rho V squared. V squared, well, that's like kinetic energy. mv squared certainly is kinetic energy. And rho here we're using mass density, so that is the amount of kinetic energy in 1 cubic meter as it comes rushing out through that hole, like you saw over here. So what that is also interpreted correctly. We can say, let's see, kinetic energy has units. What's the name we use for the units? Joules, right? Joules per cubic meter. Uh-oh, that's got 4 humps. That doesn't work. Per cubic meter. And that's going to be per, let's see, we've got joules per cubic meter, don't we? Okay, now, suppose, how fast is it moving? You can calculate it for that one that we just did there. How many of the guys did the experiment later in the day, right? You just go in the bathroom and use the urinal, you can do the same thing, right? Do it! That tells you can understand what the pressure is, right? Okay. So you have, let's see, so that says that V is 2p over rho to the square root. So 2 times 1.6 times 10 to the 6th over 10 cubed square root. 2 times 1.6 is 3 times 10 cubed to the 1/2. And here's, 3 times 10 cubed. How do we do a square root of that? 30 times 10 squared to the 1/2. So 5.5 times 10 to the 1 meters per second. So the water will come through the generator at 55 meters per second. Is that fast? How fast do you walk? 1 meter per second. How fast do you drive your car? I don't know. Okay, 60 miles an hour is 88 feet per second. So it's about how many meters a second? Say that number again.
20 to 25?
We're in the 20 to 25 range, aren't we? Somewhere right around there. Okay, so this means that this is going 120 miles an hour coming out. Do you want to get hit by that water? I don't think so. Okay, So let's see now. That's the speed it's coming out. Oh. Oh, let's do this way. The power. The power in the water. That's why we went to all that trouble. Power. The power in the water stream. Oh, suppose a 1 square meter hole. The water's coming through the 1 square meter. There's 1 by 1, right? Can you imagine? That's the hole. Does that make sense? Does it seem like a reasonable hole size for putting water on a big operation like Hoover Dam? 1 square meter. Let's just think of it in terms of that. 1 square meter at 55 meters per second. In 1 second, how far does the water go? 55 meters, right? So it goes out 55 meters in 1 second. So we have 55 chunks of 1/2 rho v squared pass through every second. Okay, 55. So we have 1/2 rho v squared times 55 equals 1.5 times 10 to the 6th. 5.5 times 10 to the 1 is about 1.5, 7, 8 times 10 to the 7th watts. That's joules per second, right? For a 1 square meter orifice. Eight times 10 to the 7th watts. 80 million watts. 80 million watts. The plant has several of these things installed on it, and its output power is about 2 gigawatts. Or if you happen to live in Massachusetts, you would say 2 gigawatts. But everywhere else says 2 gigawatts. Okay, so you get about 80 million watts, almost 100 million watts out of a square meter at the bottom, or 3/4 of the way down Hoover Dam. Put 10 of those out there, and you got a gigawatt coming at you. That's what we're using, folks. The stuff from Hoover Dam. Isn't that cool? Okay, and all of that just because you could watch that little parabolic thing right there. Okay. Now, just to keep people on their toes, if you happen to glance back and look at that clock in the back of the room, it is not correct. Okay, so just keep that in mind. Okay, so let's see. Let's do that. Let's do some temperature stuff. Let's get back on the thermal scale of things. Okay. Thermal physics. Now, Joule. Joule, the person for whom the energy unit is named. Okay, long ago, I was in the market for a wife, and so I had a date, and I asked this lady out, and we went to, she lived down in San Diego, so we went to the La Jolla Cove stuff thing there, and I knew that would be fine because I could see the wave phenomena, and we'd have the moon, so there was optical stuff, and it would be a wonderful evening. And we had dinner and walked along, and I talked about the waves and all that kind of stuff, and we had a wonderful evening. I believe in truth in advertising. And so another date we had a little bit later. This was at the point we'd already met the folks kind of thing, you know. And had her estimate the number of four-leaf clovers in this field of clover. And she lost her interest in that stuff about there. But she's a very tolerant woman, very tolerant. Because we're almost 30 years now. So yeah, it's cool. It's way cool. And she still lets me do that kind of stuff. So Joule is somebody I admire greatly because Joule, when he got married, and his wife must have been very tolerant too, or at least for a short period of time. And they got married, they went to a falls in France. Chamois Falls is what I've heard. And he thought that the water comes off the top of the falls and then it goes down. So there's a half mv squared up here, but then there's the rho gh for the delta P that should be happening. A conversion that the speed of the water is higher at the bottom now, the half mv squared increased, and then it arises that it hits the pool at the bottom and is there relatively still. Kinetic energy a little bit at the top, increased by the falls, and then the water is relatively still at the bottom. And he thought, oh, where's the energy gone? Maybe there's a little magic. Maybe it went into microscopic motion and I just don't see it with my eye. So for his honeymoon, he took a thermometer with him and he measured the temperature of the water at the top of the falls and he measured the temperature of the water in the pool at the bottom and found that the pool was hotter. That there had been a conversion then of the macroscopic kinetic energy into microscopic kinetic energy. And he associated, properly so, as we do, the concept of temperature is a measure of the microscopic kinetic energy of atoms and molecules. So temperature is now a third thing to add into our energy. We've got our potential energy and our kinetic energy. Now we've got to consider the possibility of thermal effects and allow heat flow to occur and temperature to rise and temperature to decrease. So we want to build into ourselves an understanding of a microscopic picture. Just because we can't see it with our eyes doesn't mean it's not part of the equation. And so we've learned how to measure microscopic things using macroscopic tools. And then you can actually get down on the microscopic level and measure them on individual atoms. So in my laboratory, for example, I like to use lasers, and I do plasma physics things, and with the lasers we can measure the velocity of individual ions. One ion. How fast is it moving? What direction? So we have a little, I'm going to sneeze, and that will, you guys will hope that I'm going to sneeze over here. Right? So that we can measure the speeds of all the little atoms and see that some are moving a little faster, some are moving a little slower, just like on the freeway. When you're driving along on the freeway, some of the cars are moving faster, some of them are moving slower. There's a distribution of particles. And this distribution adds up to the total kinetic energy that's on the freeway. And so the same thing happens at the molecular level, and we can measure the atomic traffic, if you wish, the atomic traffic, okay? So now, of course, when you're driving on the freeway, you have the slow pokes who are all going slower than you. By definition, anyone going slower than you is a foofnik, right? That's the technical term. They're called foofniks. So you never heard that before, did you? No, I have a Slovenian friend from Cleveland, and he says that's what his grandmother calls him. So, so anyway, the slower ones, and then there's the fast ones, right? Whoever's driving faster than you is crazy, right? That's the right interpretation, right? Okay, so the average speed of the particles, the median, the mean, these kind of numbers that are more typical of the distribution are going to be what we call like the thermal speed. So we're going to come up with a concept of thermal speed. And I'm going to say a few more words on things you should probably write down because they're probably not in your book. Let's figure out how to measure temperature. The process that I'm giving you in this class is to be self-reliant. You do not need a meter stick with you anymore for a lot of measurements. You don't need a clock with you anymore. You're able to make rough measurements on your own. Let's see if we can figure out how to do temperature. If we're going to go from here, and I'm going to go somewhere else in the country, I don't want to carry a lot of stuff with me, but I'd like to be able to measure temperature. The Fahrenheit scale, F, degrees F, has a very simple definition. Put the thermometer in your armpit. That's 100 degrees. So if you've gone somewhere and you're still living and you put the thermometer in your armpit, you can check for 100 degrees. And you can make a thermometer once you get there, stick it here, and when it reads somewhere, okay, 100 degrees. 0 degrees Fahrenheit. That's cold, right? What starts to get freezing with 0 degrees? Water. 0 degrees Fahrenheit is the coldest temperature to which a salt-saturated solution of water can be taken before it freezes. The oceans do freeze sometimes, but at lower temperatures than 32 degrees Fahrenheit, where pure water freezes, right? So if you took a bucket of water and put a bunch of salt in it, dissolved the salt, and then took the temperature down, where that froze is going to give you 0 degrees Fahrenheit. Now you can make your thermometer anywhere on the world as long as you can produce those two conditions. Centigrade, also called Celsius, is another temperature scale. Centigrade. What does cent mean? 100. Now we're starting to get sensible, right? 100 degrees. 100 degrees between two things. 100 degrees Celsius centigrade is boiling water at what condition? 1 atmosphere at sea level, right? An atmosphere at sea level. Question, sir, or not?
I thought when you put salt in the water, it lowers the temperature, so it should be lower than -32. Right?
If you put salt in the water, the act of putting the salt in may have some endothermic business going on. I don't know if that's a good term or not. That's like chemist talk. Right, but that's because of the chemical reactions that might go on. I think it does a little bit of cooling. It helps to make ice cream, I know,
It does that, yes.
right? But I don't know what that is. But once it's all in a solution, and then you take the temperature down, then it'll freeze at 0. Okay, so which is a separate issue. You're right that it does change temperature probably, but it's separate from the freezing point issue. So sea level. Atmosphere, boiling water that's pure, 100 degrees Celsius, centigrade. And 0 degrees is where pure water freezes. Now, the problem with the pure water thing is that's not so easy to get. Okay, so that you can have some reasons to go either way. I think either of those are fine. Physicists, on the other hand, this black body radiation thing I gave you a little bit of clue about, that depends on temperature above absolute 0. So I want you to imagine that you're each a molecule right now. You feeling like go? No, let's be atoms, okay? So you're an atom. Everybody, don't move. If there's no motion of anything, that's 0 degrees. The temperature is a measure of this microscopic kinetic energy. Kinetic energy is a half mv squared, so it means something's shaking. Right? Something's shaking. So now, wiggle your arms around a bit. Everybody wiggle a little. So you see how all the atoms are now doing some wiggling, right? And that's got temperature to it. So we start from the idea of absolute 0, where there is absolutely no motion, and call that 0 degrees Kelvin. Physicists normally work with whatever units are convenient for the physics they're doing. We will work with Kelvin, we will work with Fahrenheit, we will work with centigrade, whatever we want. 0 degrees Kelvin is 273.16 degrees below 0 degrees centigrade. And it has, the Kelvin scale has the same degree size as centigrade. So that means water boils at 373 degrees Kelvin. And room temperature is about 290, somewhere in that range. 290, it's a warm day, it's 290 degrees out. Okay? Now you're probably not used to thinking in terms of Kelvin, but I want you to start thinking that way. Just like using powers of 10 in scientific notation, we need to use Kelvin for a lot of our temperatures. The conversion between Fahrenheit and Celsius, you've probably seen that before. There's the 9/5 or the 5/9, the plus 32, minus 32 stuff. It's a bit of a hassle, isn't it? But you can figure it out if you remember the meaning of the temperature, how it was arrived at. Now, if you want to do from absolute 0 and use the Fahrenheit scale, you use a Rankine thermometer. People used that for a while, degrees Rankine. And I use, in plasma physics, we tend to have stuff a little hotter than room temperature, like, millions of degrees. And so we use units of temperature that have 1 unit is like 11,000 degrees. So it's a little warmer in that climate. The reason we pick the units for whatever is it's nice to work with your hands. 1, 2, 3, 4, 5. You like units that are 1 to 10 on things. Okay, now, when you do a temperature measurement, remember the thermometers that you stuck in your mouth and they have a little tube in them and you saw the silvery mercury, right? And nowadays, what are they filled with? Alcohol and red dye or blue dye or something. The mercury was so much cooler. It was fun to play with. Now, unfortunately, one time when one of our kids was sick and we still had mercury thermometers, my wife shook the thermometer, broke the thermometer on her wedding ring, and we discovered, chemists knew this, but I didn't, that gold is a sponge for mercury. It just went right into the ring. End of ring. So I had to get another ring for her. This one, the cheap one, didn't have any issue. The thermometer has a bulb in the bottom, a bulb, just like what Laura. Did I get it right? Oh, even a blind hog finds an occasional acorn. Okay, so the bulb is at the bottom and is filled with the liquid, and the liquid comes up like this. And then as you warm up the bulb, it expands the liquid. There is a thermal expansion which pushes the liquid up the tube and makes the difference in the length. Let's do some of that. Who would like to help? Oh, the volunteers, yes, I can tell. We'll do have you helped before? Okay, come on up. Come on up. Oh, you asked the thermal expansion question. No. Okay, what the heck? Oh, okay. Ball and chain. Okay, and you are?
Caitlin.
Caitlin, hi, I'm Roger McWilliams. Ball and chain, you're in charge. Okay, so now, does that ball fit through that?
No.
No? Okay. How about that one?
Yes.
Okay, so and what are the temperatures of there are two rings. One ring is too small for the ball, one ring is too big, and the ball passes through. Right? Show them again so they can tell. Okay. What I would like to do now is I'm going to heat this ring. Show them it's the one that doesn't pass through. We're going to heat that ring. And I'll bring it over here. Caitlin, come on, however, over to here, and I'm going to do the flame here. Flame torch. Yeah, do the hair back is a good idea. It only burns briefly, but it'll surprise you when it goes. And yes, I have burned all the hair off my face. But it was a fun activity. Okay, so now prove again that this ball, room temp, this ring, room temp, ball does not pass through ring. Okay, that one, yeah, but that one's out of the picture for now, I think. Let's get, does it just go somewhere? Okay, that's the one. Heat that sucker up. Just hold it there, heat it up. Oh, this flame won't go much more. And we're warming it up. So imagine this ring. Let's suppose you sort of cut the ring and stretch it out in a nice straight line. Then it's like just a stick, right? Like the thermometer. And as you warm it up, the molecules get a little more shake to them in a way that causes them to expand. Makes the length of the ring longer. Okay, let's see if the ball, go ahead, take it off, and pass the ball through. And do not touch that ring. Okay, now that's good. So it passed through, right? So we just proved that the ring did expand. Okay, now let's see now. Shall we, let's do that one off. Well, let's go over here and let's play with, howdy ho. Yeah, let's do that. I don't know. If this breaks, stand back over there. Okay, that's liquid nitrogen. So it's cold. All right? Now, let's see. The ball still passes through. That's still hot, right? How about the other one? The ball passes through that one, right? Okay, let's do this. Put them down in there, into the nitrogen. We're chilling them out now, right? So we're just chilling with physics. Okay. Let's see if the ball will pass through both of them now. Oh, it doesn't. Oh, it got stuck even almost. It does. Oh, look at that. It won't pass through either. I just want to make sure it wasn't too hot still up here to do this. Okay, so you can see we got both of them. Let them chill a little and then try to do that again. Okay, let's go ahead. So now that's the one that it could pass through, it won't. That's the one that it couldn't until we heated it. It won't pass through either of them. So when we really cooled them down, it shrunk both of the rings, and it'll get stuck there if you leave it long enough. Right? Okay, was that cool? Mm-hmm. How cool?
Very, very.
Yeah, very, very. Liquid nitrogen, 77 degrees Kelvin cool. It doesn't get much cooler than that until you really work at it. Okay, thank you, Caitlin. All right. Sir, have you helped?
No.
Come on over. We'll do a different thermal expansion one here. So this is a bimetallic strip. You are?
Miguel.
Miguel? Hi, Roger McWilliams. So bimetallic strip, two strips of metal. So they're different metal, one side versus the other. Okay? So two different materials might have slightly different properties in the way they expand or shrink as temperature changes. So let's take a look. Let's try it in that guy, see what happens. It may not work there. You know what? I know why we need to do this one. Let me add some more in there. Oh, let's do this. Balloon. Okay, show me your tongs. Okay, I take the tongs, I have a balloon, right? One balloon. We're going to put it in, down in a liquid nitrogen. That's the sound of my fingers freezing. So as it was cooled down to 77 degrees Kelvin, what happened to the volume? By how much did the volume shrink? A lot, yes. Good quantitative number. Let's go for that again. And do you suppose that the latex, the rubber, or whatever it is on this thing, the properties of that change as it gets cold? Yeah, let's find out. It does sound like it's freezing. I'm going to see if it's all that I think it's cracked up to be. Oh, balloon broke. I'm not going to grab that. That would be bad news. Okay, I forgot. Miguel?
Miguel, yeah.
Miguel. This bimetallic strip, stuff it down into the liquid nitrogen there. The two pieces of metal are welded to each other, but they're different metals. Pull it out. And what happened to the strip? See how it curved? So one side shrunk more than the other, didn't it? You got two sides, and it's now like this. One side shrank a bit more than the other, and so it's going on the inner part of the radius of that circle. Question.
What are the two metals?
What are the two metals? Does it say?
Steel and brass.
Does it make sense? Do you think it could be steel and brass?
Yeah.
You know, just because it says it doesn't make it so, right? Okay, but this does look like steel, and that does look like brass. Okay, let's go over here and play with fire. Okay? Let's warm it up. You make it more dramatic by going along the whole thing. And don't burn your fingers. Quite a bit of, in fact, you could kind of tell me something about the various thermal expansions, yes, I know, by the radius of the circle. So let's not use Miguel too hard on this, but if I look at the thing, it's about 1 millimeter thick, and it's got two materials, so they're each about 0.5 millimeter thick. How long is it? 20 centimeters. What's the radius it shrank to surround? You want to hold it again for the heat? Okay, get her warmed up. It shrank to a circle, right? And that circle's got some diameter to it. What's the radius? I can visualize it by looking at the radius. What's the radius it shrunk to?
5 centimeters.
What's that?
5 centimeters.
I think a little longer. I'd go with 10 for that, 10 centimeters. So we know the relative length of the inside and the outside to make a 10 centimeter amusing display. Right? Okay. All right, Miguel, thank you very much. Oh, we'll straighten it back out. Right? Okay, so let's write down an equation on that. Right? Check my timing. Oh, we'll have to do that tomorrow. Okay, remember, the quiz starts tomorrow at 8 o'clock.